All right, let's do this case where we have a something on a string. How's that? So let's say it's moving in a constant speed in a circular horizontal circle, but the string is making a cone as it goes around, right? So let's draw a free body diagram right here, the way it is right now. So we have a have to go this way, right? And it's moving around in a horizontal circle. So we drew a free body diagram right here. Got tension and weight. Okay? So it's moving around a circle like this. We're going to freeze it right here. Draw the free body diagram. And now let's break up this tension. Tension in the y, tension in the x, and the weight. So can we ever swing this thing around fast enough such that it's perfectly horizontal? There's no angle to the string. Is there an angle to the string now? How about now? Can we ever get it going fast enough so that it's perfectly horizontal? Look at the free body diagram. We want it to be moving in a horizontal circle, right? So it's not going up or down. It's staying at the same elevation the whole time. So what do we know about some of the forces in the y direction? They should add to 0, right? It's not moving up or down in the y direction. They should add to 0. What's going to happen to our weight? Is that ever going to go to 0? No, that's the force of the earth pulling on it, right? So what does that tell us about the angle of the string? We always have to have some t sub y equal to the weight of our object. T sub y has to equal the weight of the object. So in the y direction, we say the sum of the forces has to be 0. I used mg. There are lots of w's in physics, so I try to start using mg now for weight, because in a few minutes we're going to start talking about work. We're going to have a w for that. We have units that we use a w for. We have lots of w's. Okay, so the y component of the tension equals the weight. The weight's never going to go to 0, so we always have to have some y component of the tension. What would happen if this string went perfectly horizontal? What would the y component of the tension be? It'd be 0 at that point, right? There's no y component. It only has a radial component. So there always has to be some angle such that there's a y component equal to the weight. So we can never get it to go perfectly horizontal. Okay? Always has to be some angle such that there's a y component of the tension equal to the weight. Now, if we know the weight, this tells us what the y component of the tension is. And let's put an angle in here. Usually we measure the angle with respect to a vertical here. We'll call that theta. So if that's theta, that means that this angle over here is theta, which means that this angle over here is theta. So the y component is, what is the y component going to be? Sine or cosine? T times the cosine of theta, because the y is the adjacent side here, right? And this is theta, and t is the hypotenuse. And the x is going to be, can I squeeze it in here? T times the sine of theta. That's going to be this side. Okay? So we've got t cosine theta equals mg. That we know from our y components because it's not moving up or down. Now let's look at the radial component. Sum of the forces in the radial direction has to equal ma centripetal. And I'm going to call radially inward as my positive direction. So I have a positive t sub x, and that has to equal mv squared over r, because it's moving in a circular path. And this is t sine theta and so at this point, usually we're given, we have two equations, and so there's probably two unknowns that we can solve for. One trick here to get rid of, if we're trying to solve for the angle given a certain speed or the speed given a certain angle, that's probably what we're trying to solve for. We don't really care what the tension is in that case. So one trick is to divide one equation by the other one. Right? If you do this, t sine theta equals mv squared over r, and we divide it by the other one. And on this side, the t's cancel. We get the tangent of theta. The masses cancel, is v squared over gr. So if we were given the velocity and the radius, we could find the angle. If we're given the angle and the radius, we could find the velocity. So we'd be given a certain amount of information here. But you have two equations. You can find two things, probably an angle and a tension, or speed and tension, something like that. All right? So there has to be some kind of a force in the radial direction.